Hello viewers, Wagadaruna taking you through the story for A-Level Physics Paper 2. And this video we are going through the topic of magnetism and alternating current. In particular, in this video, we shall look at calculations involving force between two currents. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So this is what we hope to upload under this topic. What is ticked means is already available on the platform. What is not yet ticked means will be uploaded with time. And like you always know, here we are interested in calculations, but complete notes are available in the books I recommend. For physics, there are 4 books: Physics Paper 1, Physics Paper 2, Topical Question Bank and its solutions. For principal mathematics, there are 4 books still: Math Paper 1, Math Paper 2, Termly Pacifiers with Marking Guides, and Topical Question Bank. For subsidiary math, it is only one book which contains notes and past papers. And for copies of any of these books, you contact the author on this contact. Also, if you are new on the platform and you wish to get an orderly list of the videos, you can send me a WhatsApp asking for the links of the videos. I'll be sending you the ordered list so that you can watch one video at a time in an orderly way to avoid confusion. So force between two currents. In the very first video, which was on force on a current carrying conductor, we saw that if a conductor contains current, there will be a field due to that current. Okay. Now, if that conductor is placed in a magnetic field, let me say this is the North Pole, this is the South Pole. These fields will interact. The field due to the magnetic poles and the field due to the current in the conductor interact to form what we call a resultant magnetic field. That resultant magnetic field is weak at one end and strong at the other end. Therefore, a force will be created in the direction from the strong part to the weak part. That's we already saw in the very first video of magnetism. Now here, so in short, a force will always be there whenever there are two magnetic fields. What does that mean? It means that even in this case, if I have two current carrying conductors, one has current I1, another one has current I2, this one will generate a field, even this one will generate a field, meaning that these two fields will interact. And because we say that each time two fields interact, there should be a force, a magnetic force, then it means that there will be, that's where our heading comes from, force between two currents. So let us start. It says consider two parallel wires W1 and W2 carrying current. So that current can be in two forms. One can be in the same direction, or that is out of the paper, or it can be same direction but into the paper, or it can be in opposite direction. So we are going to look at both cases and see which direction gives repulsion and which direction gives attraction force. So the magnetic field of one wire interacts, this is what I want, interacts with the magnetic field pattern of the neighboring wire. Okay. So like I said, we are going to look at two cases. So case 1, if both currents are directed into the plane, into the paper, That means that they are in the same direction into the paper. The magnetic field pattern that results is as shown below. So we have wire 1 and wire 2. This X cross shows that's into the paper. I think by now you know it. So the field will be in that form, and the direction of the field is got by right hand grip rule. Same applies to this field, is in this form. Now the question is, how do you know that there will be repulsion or attraction? One, you look at this. Do you see this order here? The fields are in opposite direction. When they are in opposite direction, it means that the field will be weak. They will be they repel, so the field is weak. That is why you are seeing the fields this side are more closely packed than this side. Even here you see the field this side are more closely packed than this side. So that's what I was meaning by a force coming up in the direction from the strong field to a weak field. So if a force is to be drawn on this current, it should be in this direction. Do you know why? Because this is the direction of a weak, where the field becomes weaker. If I do this, it means that it is not okay, because here the field becomes stronger. So applies to this, the field becomes weaker in this direction. Do you see that? Now, when you see that, it means that, you see these forces, they are coming towards each other, meaning there should be an attraction. So in short, when two parallel wires carry current and the current is flowing in the same direction, there must be attraction between the two wires. So this is not a complete field. Let's draw more field lines. So here it will come as if it wants to curve this side, but it has to go this side. It comes as if it wants to come this side, but because of this direction, it has to now go this side like this. And the more it goes away from the center, the more the curvature reduces. So in this case, it means that this field is strong, this field is weak. So the force has to be in this direction. Here, this field is strong, this is weak, so force should be in that direction. And because of that, it is now called an attraction. Now, look, you should realize that the force have the same magnitude, but opposite direction. Remember that. Same magnitude, but opposite direction. Now here, because these fields keep repairing, there should be a point somewhere where the effect of the two fields cancel out. And at that point, it means that the resultant magnetic field is 0. And that point is called neutral point. So in this slide, you should realize that if current is flowing in the same direction, there should be an attraction. Okay? What if current is flowing in opposite directions? One is into the paper, another one is out of the paper. What will happen? So here we shall draw this for the first wire. Then for the second wire, it will be that. Now, do you see something here? This direction and this direction, they are pointing in the same direction, meaning here they will be we call it reinforcing, joining together. So B1 plus B2. In the previous one, it was subtraction because one was reducing the other. So here we call it reinforcing, meaning that in the middle here there is a strong field than outside. That is why you see in the middle fields are more closely packed than away. What does that mean? It means that because a force moves in the acts in the direction from a strong field to a weak field, it should go this side. Here it should also go this side. So what does that mean? It means that each time current is flowing in opposite direction, there should be repulsion. There should be repulsion. So is the summary we wanted. That straight wires carrying current in same direction attract each other, while those carrying current in opposite direction repel each other. Same direction attract, opposite direction repel. So you should remember that. Okay, so now we are going to come up with a formula which can be used in the calculation. Remember, I told you this video on this platform you're interested in the calculations, but because we can't just code the formula and start using it, that's why we give some theory background of the topic. So the theory on this platform should not confuse you and you think that you have covered completed everything. You still need the books I recommend. Okay, so magnitude of force per meter length. Force per meter length between the two wires. Why do we do that? Because sometimes the length of these wires is not given. That's why you use force per meter. It's like that if the length is given, you just multiply that force per meter times the length to give the total force. So consider two long straight conductors X and Y lying parallel and close to one another at a distance d apart, and in a vacuum carrying currents I1 and I2 respectively in the same direction. Same direction. So shall come and draw the currents X, wires X and Y separated by distance d, and the current is I1 through X and I2 through wire Y. So let us choose a point P1 on wire X and a point P2 on wire Y. In other words, we want to get the force per meter on this wire due to this, and also force per meter on this wire due to this. To do that, you need to get the flux density at point P1 due to current through Y, and also flux density at point P2 due to current through X, like that. So you shall see that the magnetic flux density at P2 due to current I1 is given by this. So flux density due to current in wire X is Bx equal to mu naught, where this is permeability of free space, I1 over 2 pi d. Now then from there, remember that force, full force is B I L. Okay, therefore force per meter will be F over L, which will now be B times I. Therefore I'll come and say that if I want to get the force at P2, force per meter on wire Y, it will be force acting on wire Y per meter is equal to Bx times I2. Bx already saw in the previous slide, multiplied by I2, you come up with this expression. So that is the expression for force per meter, meaning that if you know the length of Y, you just multiply that force per meter times L, the given length. Similarly, magnetic flux density at P1 due to current I2 is given by that, and also the force per meter will be given by that. Okay, so the force, that means that you realize that this expression is equal to this. That is why I told you that the magnitude of the forces are equal. Magnitude of the forces are equal. So I used F1, but it should be, to be consistent, you put you'll put here Fy, and here you'll put Fx. So with that, shall go through these questions. Question 1 came from UNEB 1997, paper 2, question 7D, and it says, find the force per meter between two long parallel wires 5 centimeters apart and carrying current I 2 ampere and 4 ampere in opposite directions in a vacuum. So force per meter is given by this formula, we already know it. Substitute this is the constant I1, I2, 2 pi d. So this should be in meters as a unit. And that will be the force per meter. So remember, force is a vector quantity, so you need to specify, is it repulsive or attractive? Now, because they said opposite direction, it has to be repulsive. Then question 2 came from UNEB of 2003, paper 2, question 7a, Roman 2, and says, the diagram in figure above shows two parallel wires, P and Q, placed 1 centimeter apart, and carrying currents of 10 ampere and 20 ampere respectively in the same direction. If wire Q is 10 centimeters long, find the magnetic force acting on it. So now here it means that after getting the force per meter, we can multiply by L to get the force acting. So we shall come and say that force exerted on 2Q by P will be given by this BIL. So mu I L over 2 pi d. And that is the force. It is towards P because, let us first see, was it in same direction or opposite? It was same direction. Same direction means attraction. That's why we are saying towards P. Then question 3. Question 3 came from UNEB 2002, paper 2, question 6a, Roman 3, and says, two thin long parallel wires A and B carry currents 5 amp and 2 amp respectively in opposite directions. If the wires are separated by a distance of 2.5 centimeters in a vacuum, calculate the force exerted by wire B on 1 meter of wire A. Because they say 1 meter is the same as force per meter. Or we can say length is 1. It is still the same. So constant IB, IA, L is 1 over 2 pi d. And specify the direction away. So let's see the direction of the current. They said two thin wires opposite here. Opposite direction means repulsion. Question 4 came from UNEB of 1993, paper 2, question 6b, Roman 3, and says, two parallel wires, each of length 75 centimeters, are placed 1 centimeter apart. When the same current is passed through the wires, a force of this develops between the wires. Find the magnitude of the current. So force exerted on one wire by the other is given by BIL. So B is this, IL. Because they said same current, so I1 and I2 are the same, that's why you see here I and I, because they're the same currents. So I can come and substitute the force, constant, current I don't know it, I leave it as an unknown, length I need it, I know it, I convert to SI unit, 2 pi, then there convert to SI unit. You realize that you have only one unknown, so simplify and get the square root to get the value of current they wanted. Question 5 came from UNEB 2016, paper 2, question 5b, Roman 1, and says, figure 2 shows two wires AB and CD of length 5 centimeters each, carrying a current of 10 amp in the direction shown. A long conductor carrying a current of 15 amps placed parallel to wire CD 2.0 centimeters below it. Calculate the net force on the long wire. Calculate the net force on the long wire, which is this. So we shall come as that force on the long wire due to current in CD. It will be BIL1, where B is the flux density on the long wire due to current in CD, and I is the current in the long wire. L1 is the distance between C and D. So substitute constant is this, current through CD is this, current in the long wire is 15, CD is this converted to meters, 2 pi, and D1 is this. So there you can get the force, and also get the force in the long wire due to current in AB to be B2IL2, where B2 is the flux density on the long wire due to current in AB. I is the current in AB, and L2 is the distance between A and B. So come and substitute the constant I2. Remember they said wires AB and B and CD carry the same current of 10 amp. That's why you still use 10 amp here. Current in the long wire, distance AB, 2 pi D2. So one is towards CD, the other one is away from AB. Meaning that we get by subtractions either in opposite direction. And because this is bigger than this, it means that the final direction will be this. That's why you see it here. So question 6 came from UNEB 1992, paper 2, question 6D, and it says a wire XY rests in a horizontal non-conducting cable. Rests on a horizontal non-conducting cable, which is this, and another wire PQ of length this is free to move vertically in guides at the ends P and Q, can move either up and down above XY as shown in the figure. The mass per unit length of PQ is this. Okay. A current of 3.6 ampere through the wires was enough to maintain PQ at a distance of D centimeters from XY. Okay. Calculate Roman 1 the distance of separation D, and Roman 2 the magnetic flux density due to PQ on XY. So that means that here they should be, actually, yeah, you see this? They are in opposite direction. And opposite direction, we said there is repulsion. So here there is a repulsive force. But also, this wire has a mass, therefore there should be a weight. So that there's going to be a force and also a weight. And because it is in equilibrium, upward force should be equal to downward force. So let's go and show the forces on the wire. So that was what was given. Here there will be weight, and there will also be an upward force due to the current in wire XY. So mass, they said mass is, you convert, let's see here, they said that wire PQ is 3 milligrams per centimeter. So we have to go back and ask, what is the length of wire PQ? Wire PQ is 12 centimeters. So when I multiply 12 by 3, I'll come up with milligrams. Then I convert the milligrams to kilograms to give you 36 exponent negative 6 kilograms. So at equilibrium, F will be equal to mg. So what is F? F will be force. It is no longer now force per meter, it is force. That is why there is this L here. Okay, then make D the subject and substitute. Use a calculator to come up with the separation they wanted. Then Roman 2, they wanted the flux density due to P2 on XY. Flux density on XY due to P2. So B will be equal to that, substitute and get the answer they wanted. That was question 6. Question 7 came from U.A.C.E still, 2017, paper 2, question 5e. It says, figure 2 shows an ampere balance. Wires AB and CD, each of length 100 centimeters, lie in the same vertical plane and are separated by 2 millimeters, which is here. When a current I is passed in opposite directions through the wires, a mass of 0.3 grams is placed in the pan to obtain balance. Okay, find the value of the current I if P2 is equal to QR. If P2 is equal to QR. So one should realize that because of this mass, there is a downward force. Okay, even here, because of repulsion, opposite direction, the force is here. That means that at balance, the moment, which is anti-clockwise, should be equal to the clockwise moment. So you come, let us redraw and show the forces. So there will be a weight and there will also be a repulsion there. So at equilibrium, when you take moments about 2, we shall come up with F times 2, F times 2R is equal to mg times P2. But the good thing, we know that 2R is equal to P2, so these two can cancel and remain with F equal to mg. And I know that F is the force between two currents, so it will be given by this formula. Then I can make I the subject and substitute, then get the answer they wanted. Then question 8 still is from U.A.C.E 2012 but to question 5D and says, two parallel wires P and Q, each of length 0.2 meters, carry currents of 10 amps and 1 amp respectively in opposite directions as shown in the figure below. The distance between the wires is 0.04 meters. If the wires remain stationary and the angle of the plane with the horizontal is 30 degrees, calculate the weight of wire Q. Okay, so what you are going to do, we are going to draw them, seeing them from a side, and this is what we are going to see. Shall see that? Well, this one means into the plane and this one means out of the plane. Because they are in opposite direction, there should be a repulsion. Remember that. So let's begin with this, because this is the way they want. So you shall put your W, then you could resolve it parallel to the plane and perpendicular to the plane. Then there should be a normal reaction and a repulsive force due to this current. So that repulsive force is given by this formula, we already know it. Substitute and get the force. After that, we shall now say, if the wire remains stationary, it means that when I resolve parallel to the plane, for wire Q, it means that forces up the plane should be equal to forces down the plane. Therefore, W sine 30 should be equal to F. Come and substitute for F and remain with W as the only unknown. So make it the subject to come up with the answer they wanted. Then question 9 came from UNEB 2015, paper 2, question 5B, Roman 2, and says, 3 conductors, PQ and R, carrying currents, these ones, respectively, are arranged as shown in the figure below. Calculate the force experienced by the conductor P here. So there'll be a force experienced here due to this current, and also force experienced at P due to this current. So I'll come and first redraw. So I think you remember that opposite direction it is repulsion and same direction it is attraction. So here there will be a repulsion. Force at P due to current at Q is a repulsive force. Then force at P due to current at Q is an attractive force. So remember that's the formula for force per meter. Therefore, force per meter at P due to current at Q is given by this, which I substitute in this formula, and to be this, which is repulsive. That's why you see it here. Then also the force at P due to current at R is attractive, and it is 2.4 exponent -5. Now I have to resolve vertically and horizontally, after which I can get the resultant. So resolving horizontally, I'll come up with this as horizontal component. Resolving vertically, I'll come up with this as the vertical component. So resultant force is got from Pythagoras theory. And then remember, force is a vector quantity, so you have to get the direction. So positive horizontal, negative vertical means downward. Then you join from start to end, which will be the resultant. Therefore, tan theta will be equal to opposite over adjacent. Using a calculator, theta will be that. Then you can conclude that the resultant force per meter at P is this in the direction this below the negative horizontal. Then question 10 says, the diagram in figure 3 shows 3 infinitely long, straight, and parallel wires, P, Q, and R, placed at the corners of an equiangular prism of side 2 centimeters in air. The currents flowing through the wires are this, and this respectively. Okay. Determine the force per meter acting on wire Q. So mean that we have to look at it through this side, and we redraw the diagram. So shall come. Equiangular means equal angles. So same direction of current means attraction, opposite direction means repulsion. So here there will be a repulsion due to this because it's opposite direction. Then here there will be an attraction due to this because of same direction. Force per meter formula is there. Then you can get the force PQ as repulsive, and also force PR, it is attractive. Then I can get resolve in order to get the resultant. So when I resolve horizontally, the horizontal component will be given by this. Resolve vertically, the vertical component will be given by this. So because this is 0, it means that the resultant force is entirely vertical. So the resonant force is this in the positive y direction, and that's what they wanted.